So, this is our lecture on planes. I talked a little about it in class the other day, but let's go over the theory again real quick. The basic idea is that a plane is two-dimensional and there is a vector coming out of it perpendicular. That vector is called the normal. You can see it on your notes here, this n. And that means that if I pick an anchor point here, x naught, y naught, z naught, or r naught, and then I pick any second point in the plane, the vector between them will be perpendicular to the normal. So we're saying any x, y, z minus the anchor point dotted with n will give you 0. Once we have all that worked out, we can expand it to get a scalar equation. We have n as ABC, and we said the RT minus R naught we can write as x minus x naught, y minus y naught, and z minus z naught, where the x, y, z correspond to any point on the plane. Now, you can leave it in this form. This is perfectly fine. That's the point slope, or I guess point normal form. But while this is fine and it can be used with any points, it also means that if two different people chose two different points, they will get two different equations, even though they're equivalent. So you might want to expand it out to this form: ax plus by plus cz plus d equals 0, where x, y, and z are in R. This is kind of like in two dimensions. You have the point slope form, which is this, or the standard form, which is this. And if I just said write an equation of a plane, either one would be acceptable. In 2D, we also have the slope-intercept form, the y equals mx plus b, so you could solve this for z if you wanted to, but there's no real reason, so we won't. So, a simple example here: if the vector is based at the point 0, 3, 2, find the equation of plane. Well, that means we have the normal vector. This vector is supposed to be a normal vector. Another typo, I guess. I apologize. But 2, negative 1, 3 is a normal vector. And so we then plug it in with this point. We would then get 2x minus 0 minus 1, y minus 3, plus 3, z minus 2 equals 0. Or if you want to expand this, 2x minus y plus 3z minus 6 equals 0. Then we could combine the constants to get 2x minus y plus 3z minus 3 is 0, or 2x minus y plus 3z equals 3. So those are the two forms. They are equally good. Let's move on to the next one. All right. So now we say 3 points. So a line is defined by 2 points. If you have 2 points, that's the only line that goes through them. A plane is defined by 3 points. If we know there are 3 points on the plane, there is only one plane that could fit it. There are more than one ways to write the equation of the plane, but all the different ways you write it will be equivalent. And so the basic method is you go from 3 points to 2 vectors to 1 normal. So that means these 3 points, we want to work out vectors between them. So P is 1, 3, 2, Q is, you see it. Well, then we get PQ is 2, negative 4, 4. And PR is 4, negative 1, negative 2. And there's also QR is a third vector. Plus, you could reverse the order of any of these. But you only need 2 of them. So once you have those 2, you then need a normal vector. Well, a normal vector, by definition, is perpendicular to every vector in the plane. So that means we can get it by taking the cross product of these two vectors. That's one of the main uses for the cross product, is to find a vector that's perpendicular to two other given vectors. So we get 2, -4, 4, 4, -1, -2. Which we then expand out. We get I, -4, 4, -1, -2, minus J, 2, 4, 4, -2, plus K, 2, -4, 4, -1. Which then comes out to I of 8 minus -4 minus J of -4 minus 16 plus K times -2 minus -16. Which then comes out to 12I plus 20J plus 14K. So that's our normal vector. That's the hard part. So now all we need to do is just write it out and shift it to have one of the points in it. So I'm going to choose to use the 1, 3, 2, but you could use any of them. We get 6 x minus 1 plus 10 y minus 3 plus 7 z minus 2 equals 0. Quick pop in to note, I scaled down the vector here, divided everything by 2. You can do that since we just need a normal vector, so any parallel vector will suffice. On editing, I noticed I forgot to explain that. I'm worried I might have confused someone. If you want to expand this out into right standard form, and the reason why you might want to do that is because that way it's unique, or at least closer to it, depending on if you factor properly. You could have used the P, the Q, or the R here, but if we expand this out, 6x minus 6 plus 10y minus 30 plus 7z minus 14 is 0. So 6x plus 10y plus 7z minus 50 is 0. Or 6x plus 10y plus 7z equals 50. That would be the equation of the plane, the standard form. If, for instance, that 7 were an 8, if everything were even, we'd probably divide everything by 2. But right now, there's nothing we could divide everything by, so this is as simple as we can get. And the idea is, if 3 different people started, one used P, one used Q, one used R, once we collected all the like terms, we would get the same equation. We would have that 50 on the right. So that's our idea. And if you want to check this, you could plug in all 3 points. For instance, R was 5, 2, 0. If you plug that in, 6 times 5 is 30, 10 times 2 is 20, 7 times 0 is 0, 30 plus 20 plus 0 is 50. And if you checked P and Q also, and all 3 of them worked, you would be guaranteed that's the right equation. Because as we said, there's only one plane that all 3 points are part of. So if you test all 3 points and they all work, you will know you had the right answer. So if on a test, for instance, I were to say find a plane that goes through these 3 points, you'd want to, at the end, plug in all 3 of them to see that they all worked. You could check right now, plug in 1, 3, 2, and plug in 3, -1, and 6, and see that they would also work. Okay, so let's go on to another one. This is sort of the most typical example of a problem you would get on this. I'll just find the equation of a plane. So let's go to some that's a little less typical. Okay, what's next? The intersection of a line and plane. So a line will probably hit a plane unless it just happens to go parallel to it. But assuming that's not the case, all we really need to do here, since our line is parameterized in terms of t, is to plug in each variable with its expression of t. So we replace the x with 2 plus 3t, the y with negative 4t, the z with 5 plus t. If the equation weren't already written in parametric form, you would probably need to put it into that form first. That way you could have everything in terms of t. There'd only be one variable. So let's see how we do this. Well, we want to say L was 2 plus 3t, y is negative 4t, and z is 5 plus t. So then the plane was 4x plus 5y minus 2z equals 18. So we're going to plug in each of those. And if you never learned this rule when you took algebra, learn it now. Whenever you plug in, you always use parentheses. There are maybe some examples where you can get away with not doing it, but you should do it anyway because it can be hard to tell when you get started whether you need to or not, so you might as well just do it anyway just to be safe. So 8 plus 12t minus 20t minus 10 minus 2t equals 18. Let's solve this for t. We'll combine, we'll get us negative 10t minus 2 equals 18. So negative 10t equals 20. And therefore t equals negative 2. So that essentially tells us when the line hit the plane. It hit 2 seconds before we started paying attention. So now that we know what t is, we can plug it in to L to get where it hits the plane. So let's plug in negative 2. So x of negative 2 would be 2 plus 3 times negative 2, or 2 minus 6 is negative 4. Y of negative 2 would be negative 4 times negative 2 is 8. And z of negative 2 would be 5 minus 2 is 3. So the answer to this problem would be negative 4, comma 8, comma 3. That is a point that is in both the line and the plane. And you could plug it in to check like we did before. The plane equation was 4x plus 5y minus 2z is 18. You could say 4 times negative 4 plus 5 times 8 minus 2 times 3 is negative 16 plus 40 minus 6 is 18. So that's on both the line and the plane. I guess it's possible that the line would not hit the plane at all, and if that were to happen, then probably all the t's would cancel when you tried this problem, and you would get no solution. It's also possible the line is in the plane, which is every point is an intersection. We could rule that out pretty quickly if we just, for instance, plugged in 0 for t and see that that would not work when we plugged into the plane equation. We'd have 2, 0, 5, and that wouldn't... Yeah. So, in most cases, this will give you a single solution. Alright, what's next? We want to find the intersection of two planes. So what would that look like? Well, we would have one plane, and then we'd have another one at some sort of angle to it. And it would turn out there would be a line where the two meet. Something like that. Maybe you can visualize it better than I can. Let me see if I can erase that. Try to imagine, yeah, sort of two little wings that are intersecting, two little pieces of paper slice across each other. There'll be this line in the middle where they are sort of on a hinge. How are we going to find out what that line is? Well, there are a few ways to do this. One way is just be sort of guess and check, because if we can get 2 points that are in both of them, that would be enough. But that can take some work. I wouldn't necessarily advise it. You can try. But let's do this. All right. P1 is x minus 2y plus z equals 0. And P2, 2x minus 3y minus 2z equals 0. So we're going to want to do a parametric equation here. We're going to need a parameter. And so what we generally want to do is just pick one of the variables to just be t. Let's just say x equals t. You could do y equals t or z equals t if you preferred, but yeah, we usually do x equals t. And then I want to try to write equation with y and x only. So let's see if we can get rid of the z. Well, we will use some standard techniques here. We'll multiply p1 by 2. So it'll be 2x minus 4y plus 2z equals 0. And 2x minus 3y minus 2z equals 0. Add these together, we get negative 7y plus 4z equals 0. Solve for y. Well, that would give us y equals 4 over 7 x. Now we said we're replacing x with t, so we'll make it 4 over 7t. If you were to leave it as x, I mean, I guess it would technically be right, but we want to think of it as being time, so we're going to replace with t when we can. So that gives us y. So let's see what we've got here. We've got x is t, and let's... What did I just hit? We've got x is t, and we've got y equals 4 over 7t. Now z, we could do the same thing as we did before, try to eliminate a y, but it's not necessary at this point. We just take either equation and plug in. Let's say for P1, we have x is t minus 2 times y is 4 over 7t plus z equals 0. So then we get t minus, this is 2 over 1, so 8 over 7t plus z equals 0. So negative 1/7 t is z, or negative 1/7 t plus z equals 0. So z equals 1/7 t. So that's an equation of the line. Those are parametric equations. X is t, y is 4/7 t, z is 1/7 t. If we want to check, as always, we plug back in. P1 would become t minus 2 times 4 over 7t plus 1 over 7t is t minus 8/7 t plus 1/7 t is t minus 7 over 7t. That's just t minus t is 0. So that is in P1. And then for P2, we would say 2t minus 3, 4 over 7t minus 2, 1 over 7t is 2t minus 12 over 7t minus 2 over 7t is 2 is 14 over 7t minus 14 over 7t is 0. Check. So both of them were supposed to give 0, and they both did. Therefore, this line is in both planes. So unless these happen to be the exact same plane, there's really no other line that would have worked. Okay. Let's keep moving. Okay, now we're going to do something else, which is the distance to a plane. This is a little tricky here, but it's not that bad. The idea is, first off, we've got some point in space. We'll call it Q. We pick some point on the plane. Now the P, the point on the plane, does not matter what it is. It shouldn't, because we're trying to get the distance. Think of the plane as the ground, and you let loose a ball, and you can pretend the Earth is flat as long as you're not going too far. You let go of the ball and it drops straight down at a right angle to the ground. We want to know how far that is. So the distance will always be a right angle. Well, we say this distance here would be the same as this distance here. This angle theta is adjacent to the distance. So distance would equal to this length of this hypotenuse, PQ, times the cosine of theta. And so we end up with this formula here, the component formula. So then in terms of technique, what we're saying is distance to plane. We are given a point Q. Pick any point P on the plane. That's step one. Step two would be calculate the vector PQ. And then you have a formula here that you can use, which is the distance is the same as a component formula, and so it comes out to the length of the normal vector, which is in the equation of the plane, times the length of PQ, times cosine theta over n, or just PQ dot n over length of n. And this should be absolute value because it could come out to be negative, but distance always positive. So if you just want to memorize the formula, that's it. But it comes from this geometric figure where we say the angle is adjacent to both the vertical distance and this slant distance. So let's do an example here. My distance of the point Q equals 1, 5, negative 4. From the plane, 3x minus y plus 2z equals 6. Well, we have one point. They gave us a point. And the plane was 3x minus y plus 2z equals 6. So we need to pick another point. So you just look at this. You say, well, what's a set of x, y, z that would make this true? And I'm going to go with 2, 0, 0. The easiest way usually is to make two of the variables 0 and just solve for the third one. You could use 0, negative 6, 0. You could use 0, 0, 3. And there are lots of other things you could use too. But we try to keep it as simple as possible. So what then is the vector PQ? Well, it's negative 1, 5, negative 4. And the normal vector, we just read off the coefficients of the plane equation, 3, negative 1, 2. So then the distance will be 3, negative 1, 2, dot, negative 1, 5, 4, negative 4, with absolute value if we need it, over the length of n. And the idea with the length of n thing, because we've got this, like I said, PQ dot n over length of n, is that the normal vector, we don't know how far away it goes from the plane, and that shouldn't matter, so we end up dividing it out. And so we get on top 16, that's negative 3 minus 5 minus 8, so 16 over square root of 14. That's the distance from the plane. What if, on the other hand, we want a distance from a point to a line? It's a similar idea, but look at the graph this time, and you'll see this time the theta is opposite the distance. So if we have a line, and we want to know how far the point that we're given, Q, is from the line, we use the cross product instead. PQ cross V over length of V. Note again, P doesn't matter. We can pick any point as long as it's on the line. So use whichever one seems most convenient to you. So our example here, find distance from the point Q is 3, negative 1, 4 to this line. So the easiest way to get a point P would be just plug in 0 for T. So let's do that. So if T equals 0, we get P as negative 2, 0, 1. All right? Yeah. So then PQ would be 5, negative 1, 3. And then we want V, the vector of the line, to be 3, negative 2, 4. And I guess if you're wondering what the difference between these problems is that in this case we are picking V as a vector on the line, whereas the plane we're picking a vector coming out of the plane. And so the fact that it's going with the line is why we use cross product this time, whereas for the plane it was going perpendicular to the plane, so we use dot product. So that's why they're different. All right, so let's plug it into our formula here. It's a pretty simple formula. We just need to cross these and then divide by the length of V. So let's see, I, J, K, 5 minus 1, 3, 3, negative 2, 4. So it's I times, well, yeah, let me show the steps here. Still trying to show all the steps at this point. Negative 1, 3, negative 2, 4, minus J, 5, 3, 3, 4, plus K, 5, negative 1, 3, negative 2. Which gives us I of negative 4 minus negative 6, minus J of 20 minus 9, plus K of negative 10 minus negative 3. Which comes out to 2I minus 11J minus 7K. So we need the length of that, 2I minus 11J minus 7K, divided by the length of V. Again, the reason why it's V is because if we were to rescale this line so it was going faster, it shouldn't matter. So we're saying we don't want how long the velocity vector is to affect it. Only the PQ should still be there. Divided by the length of V is, let's see, what was V? It was 3I minus 2J plus 4K. So that gives us square root of 4 plus 121 plus 49 over square root of 9 plus 4 plus 16, which is square root of 174 over square root of 29, which happens to reduce to square root of 6. So that's our answer. That's the distance. Okay, let's look. We got just a little more. We're almost done. If you want to pause and work the problems in the homework that are covered by what we've done so far, that might make sense, and you can come back and finish this later. But assuming that's already been done, if we have two parallel planes, there should be a distance between them. And we want to find out what that is. So let's take these two equations. The idea here being, well, we've got a first plane. We've got a second plane below it. Let's not do it like that. Well, if the distance of them would be based on the perpendicular vector. So this would be normal to the first plane, but it would also be normal to the other plane. Let's call that negative n, I guess. It doesn't really matter which one is your positive and which is negative. But the point is that we could use the same distance formula. If we have a point on the one plane and a point on the other plane, we could say what is distance between the two planes using the same formula we did just before. So let me clarify here. What were our planes? We had 10x plus 2y minus 2z. So let's use the point 1/2, 0, 0 for the first plane, and let's use the point 0, 1, 0 for the second plane. Again, we try to keep everything zeros. So I looked at this one, I thought the easiest thing to do would make x be 1/2, and here these thing would be for y to be 1. So we're just going to pick 2 points. P1, we have a point 1/2, 0, 0, and P2, we have a point 0, 1, 0. So what we are saying is that the distance from 0, 1, 0 to the plane 1 is the same as the distance between the planes. Okay? So that means we can use the same process. We can say the PQ will be the distance between those 2 points, or the vector between the 2 points, which would be negative 1/2, 1, 0. Again, if you subtract them in the opposite order, it would be the opposite sign, but it would all end up the same. And the normal vector would be 10, 2, negative 2. You could use the 5, 1, negative 1 if you want. However, in this case, I'm using the 10 because I'm looking ahead to 10 times negative 1/2 will get rid of the fraction. So the distance would be negative 1/2, 1, 0, dot, 10, 2, negative 2, over the length of 5, 1, negative 1. And that'll come out to, on top, it'll be 5 plus, negative 5 plus 2 over square root of 27. That's, we'll put absolute value on that, 3 over 3 root 3, or 1 over root 3. Okay, so that's that. Last problem, and this one, the geometry of this, I find hard to visualize, so I'm just going to have to kind of say trust me on it. But the idea is that if we have 2 lines that are skew, they must both be in planes that are parallel. And again, I have trouble explaining why that is. But, there's a picture in the book about it. But, yeah, we've got a line here, and a second line going this way, that there must be some plane they lie in. There are lots of planes any line lies in. There's infinitely many, but we sort of rotate them in such a way that they are parallel. So, like I said, I'm not really good at explaining that one. You'll just have to trust me on it. We have a vector vector 1, 3, negative 1. That is a vector for the first line. And a vector 2, 1, 4. That is in the second line. These are both vectors that lie in the hypothetical planes, where each one has its own plane. So the normal vector must be perpendicular to both of these lines. That is to say, we've got two parallel planes like before. There is a normal vector between them. It's perpendicular to both of them. Well, if the first vector is in this plane, and the second vector is in this plane, this normal vector must be perpendicular to both, so we can find it by doing the cross product. So the normal would be the cross product here. At this point, I'd say you can work the cross product on your own. It should give you 13i minus 6j minus 5k. That's a cross product. Now we need a point to determine, well, we need a point from each plane, right? That was the rule. We needed PQ, that is distance from a point in one to a point in the other. And then we need a point in, and then we need the normal vector. So, we've got our two equations. Let's put in 0 for both of them. So if I put in 0 for t, I get 1, negative 2, 4. If I put in 0 for s, I get 0, 3, negative 3. So we now have our 2 points. Plug in 0, get 1, negative 2, 4. And that's P. And Q is 0, 3, negative 3. So the vector between them, PQ, equals negative 1, 5, negative 7. And the normal vector we found was 13, negative 6, negative 5. Now the textbook does this a different way. It uses a formula, but let's do it the way we did earlier. So the distance would be the dot product of these divided by the length of n. 13 squared plus 6 squared plus 5 squared. I'll take absolute value on top if we need to. So this will give us absolute value of negative 13 minus 30 plus 35 over square root of 230, or 8 over root 230. That's the answer. Now you notice I did differently than in the book. The book has a formula they did, and I want to clarify something that I alluded to earlier, but maybe wasn't as clear as I could have been. When I write out an equation of a plane, this is the standard way the book would do it, with the D on the left. Now, some other places would say the standard form would have the D on the right, moved to the other side. And it changes. The problem there is that that would change the sign about which side it's on. So, for the purpose of our class, we'll consider this the standard form with the D on the left. That's important in particular if you want to use that shortcut the book gave, which is the distance from the point x1, y1, z1 to the plane ax plus by plus cz plus d equals 0. In that case, you could try to work this out directly. You would get, if you use the formula we just did with the dot product, and you could do a little bit of algebra and show that you can reduce it to this new form over square root of a squared plus b squared plus c squared. I would not recommend trying to memorize this formula. I think that's unnecessary work. However, it might be an interesting exercise to try to show why this works. Right, work out using this point x1, y1, z1, use the method we used with distance of the plane and the dot product, and show that it turns out to be this same thing. But you don't have to. You can use either method. Thank you. I'll see you Tuesday.